Let's try to understand wave. I mean wave in the mathematical picture because I think the wave equation is given by the mathematician.
Yes, absolutely. When we say wave in a mathematical sense, we're usually talking about a wave equation. That's a partial differential equation that describes how a wave moves through space and time. Whether it's sound, light, or even a quantum wave function, the mathematics captures how the shape of the wave evolves. It's a gorgeous intersection of physics and mathematics.
How the shape of the wave evolves. Okay, and that waves moves through space and time. I think that two things are very necessary condition for the wave, spatial and temporal part.
Exactly. The wave's shape evolves both in space and in time. Mathematically, you often have a function of both position and time. The spatial part shows how the wave stretches or compresses across space, while the temporal part shows how it oscillates or propagates through time. Both are essential to describe any wave phenomenon, whether it's a ripple on water or an electromagnetic wave zipping through space.
Oscillations are the application of the wave.
Oscillations and waves are definitely close cousins. Oscillations happen when something moves back and forth in time. Think of a pendulum. A wave is basically what happens when you let that oscillation travel through space. So oscillations are like the local building blocks, and waves are those oscillations moving through a medium or field.
But what was the first time that they think and capture that mathematical picture and wrote down the wave equation?
The first major step was in the 18th century. Jean-Laurent d'Alembert, in 1746, wrote down what we now call the one-dimensional wave equation to describe vibrations on a string. From there, others like Euler and Lagrange expanded it. It was a foundational moment connecting physical vibrations with mathematical descriptions, the birth of wave equations as we know them.
This Jean Lee Ron D. Alembert in 1746 wrote down the one-dimensional wave equation to describe vibration on a string. Uh, what was his motivation to work on this thing?
D'Alembert was driven by a broader quest to understand mechanics and motion, a major theme in 18th century science. Strings and vibrating bodies were central to music and engineering. He wanted to rigorously explain how these vibrations worked. Plus, at the time, there was a push to express physical phenomena with calculus. Newton's ideas had taken hold, and the mathematical tools were ripe for explaining real world motion.
Hmm. So, uh,
If there's another angle you're curious about, or you want to dive deeper into the math, I'm right here. Just let me know what direction you'd like to explore next.
so he wanted to know how this vibration work and push this physical phenomena with calculus. So Newton ideas also had taken hold and mathematician tools. Okay, calculus was not actually okay. Calculus has developed at those time actually.
Yes, exactly. By then, calculus was pretty well developed, largely thanks to Newton and Leibniz in the late 17th century. By D'Alembert's time, calculus had become a powerful tool, and he used it to bring rigorous quantitative understanding to physical phenomena like those string vibrations.
And what next after that? Why? So he take the simple case of 1D.
Exactly. He started with the simplest case, one dimension, like a vibrating string. After that, others, like Euler and Lagrange, generalized the wave equation to other shapes and higher dimensions. It paved the way for understanding sound, light, and even quantum waves. So one simple vibrating string started a whole revolution.
But what about this? Why not he himself expand those to 2D, 3D, and with time also?
Well, the 1D case was already a huge breakthrough, and it was the natural starting point. Tackling higher dimensions adds complexity, more variables, more intricate solutions, but he laid the foundation. Soon after, others like Euler and Lagrange did generalize it. Science is often a relay. D'Alembert passed the baton, and others took it into new dimensions.
But how did he verify its 1D case?
In his time, verification was more conceptual than today's rigorous experimental methods. He compared the equation's predictions to known patterns of vibrating strings, like musical instruments. If the math mirrored the observed harmonics and nodes on strings, that was success. In fact, his equation beautifully matched known vibrational modes, so the theory and observations resonated, literally.
But okay, you are telling that like musical instrument, if math mirrored the observed harmonic and notes on string, that was success. Can you explain that part a bit more?
Sure, when you pluck a string, it doesn't just vibrate randomly, it forms patterns. You get a fundamental tone and higher harmonics, which are like neat divisions of the string's length. D'Alembert's solution matched those patterns. His wave equation predicted these standing waves, with nodes where the string doesn't move and antinodes where it does. Seeing that math align with real vibrating strings, like on a violin or a monochord, was strong evidence he was on the right track.
So, math align with the real vibrating string like a violin or a monochord with strong evidence he was on the right track. The Alembert solution match those patterns. His wave equation predicted these standing waves. So basically, his wave equation actually predicted the standing waves. Okay, can you explain that part?
Absolutely. A standing wave is when the wave doesn't appear to travel but oscillates in place. Think of a string fixed at both ends. The wave equation predicts certain modes, frequencies, where some points stay still and others antinodes oscillate at maximum amplitude. D'Alembert's equation predicted exactly those patterns, showing the stable repeating oscillations that match the harmonics we hear or see. That was his triumph, capturing the natural music of vibrating objects in math.
Repeating oscillations that match the harmonics.
Exactly, those repeating oscillations form the harmonics. Each harmonic corresponds to a different standing wave pattern. The fundamental frequency is the simplest one, then you get overtones. So he didn't just explain one vibration, he laid the groundwork for understanding all the complex patterns we see and hear in vibrating systems.
Vibrating system, what was that?
A vibrating system is just anything that can oscillate back and forth. It could be a string, a drum head, a tuning fork, or even atoms in a solid. When disturbed, it moves around an equilibrium position. The wave equation describes how that motion happens, whether it's on a string, in air as sound, or in water as ripples. So any system that can repeatedly move back and forth, yep, that's a vibrating system.
The fundamental frequency is the simplest one. Then you get overtone. So, can you explain that part and what is the meaning of overtone here?
Of course, the fundamental frequency is the lowest frequency at which a system vibrates. It's like the main note you hear on a guitar string. Overtones are the higher frequency vibrations that occur at the same time. They're multiples of the fundamental frequency. So the string might vibrate in halves, thirds, and so on, producing richer sounds. These overtones combine with the fundamental to give the overall tone its character.
Overtone combines with the fundamental to give the overtone its character. What was the fundamental frequency meaning?
The fundamental frequency is the lowest natural frequency at which something vibrates. It's like the bass note. If you pluck a string, the simplest vibration, where the entire string moves as one segment, gives you the fundamental. It sets the primary pitch. All the overtones are just neat multiples of that fundamental frequency.
Okay, what next?
Well, from understanding those simple vibrating systems, scientists moved on to more complex waves 2D surfaces, 3D spaces, and eventually fields like electromagnetism. And today, that same wave equation idea helps describe sound, light, quantum particles. Waves are everywhere. If you ever want to dive into any of those next steps, I'm happy to explore with you.
So why did the this PD capture that wave? Why not other mathematical picture? One short answer, just.
Because waves depend on both time and space, how they move and change everywhere. A partial differential equation is perfect for that because it relates how things change in space and time simultaneously. It's like the natural language of continuous traveling phenomena.
Okay, can you make conclusion what we have discussed?
In short, we traced how D'Alembert's wave equation emerged. He used calculus to describe vibrations, like a plucked string predicting standing waves. His math matched real harmonics, validating the model. From that 1D start, others expanded to 2D, 3D, and beyond. Ultimately, partial differential equations captured waves perfectly, and this foundation now explains everything from music to quantum mechanics.
Yeah, thank you.